Welcome to Algebra, Special Case Trinomials, Part 2, Difference of Squares. In the last video, we learned about a special type of trinomial in which the product of two identical binomials creates a perfect square trinomial, such as these. We observed a special pattern in which the two outside terms of the result were the perfect squares of the two terms in the binomial, and the middle term was double the product of these two values. These four examples were a few of the perfect square trinomials we explored. Take a moment, pause the video if you need to, and review this pattern. Now we look at another special case trinomial where the result is called the difference of squares, a classic pattern in algebra. Shown here is the simplest example of this pattern. The two binomials, x plus 1 and x minus 1, are identical, except they have opposite operators. One has plus, the other minus. See the final result, x squared minus 1, a difference of two square values. Technically, it is a trinomial, even though the middle term is missing. It was 0x, but when something is multiplied by 0, it just drops out, since anything times 0 is just 0. It doesn't need to stay in the expression. Let's work through the FOIL process to see how this happens. The product of the first terms, x times x, is x squared. The product of the outer terms is x times negative 1, negative 1x, or just negative x. The product of the inner terms is 1x, or just x. The product of the last terms, positive 1 times negative 1, is negative 1. The two middle products, negative x and positive x, combine to be 0x, which disappears in the final expression, leaving x squared minus 1, the difference of two square values, hence the term difference of squares. Let's look at another one, x plus 2 times x minus 2. Again, the final expression only has two terms, but is technically a trinomial since the middle term is 0x. It drops out for the same reason as we mentioned in the last example. 0 times anything is 0, and does not need to remain in the expression. Again, we check out the FOIL process and see a similar result. The first terms multiply to make x squared. The two middle terms end up to be opposite values, negative 2x and positive 2x. And the last term is negative 4, the product of positive 2 and negative 2. The middle two terms combine to equal 0x, which drops out, and the final result is the difference of two perfect squares, x squared and 4. Here are a few more examples where the first terms are not 1. However, the pattern remains the same. The resulting first term is the square of the first term. In this first case, the value 2x squared results in 4x squared, and the second value 3 squared equals 9, which is negative since the values are opposite. The middle term disappears, leaving the difference of the two squares, 4x squared minus 9. Let's look at these next examples. Think about the answer for each, and then see if you got it right. Pause the video if you need more time. 3x minus 5 times 3x plus 5 fits the pattern, and the result is very simple. 9x squared minus 25. The perfect squares of each term subtracted. Here we have 4x plus 2 times 4x minus 2. The result is the squares of the two value, subtracted, 16x squared minus 4. This next example shows the same result, the difference of the two squares of the binomials, 25x squared minus 81. The last one again follows the same pattern, 49x squared minus 1. Now that we know the pattern when the difference of squares product is created, let's try factoring a difference of squares binomial back out to the original two binomials. We'll start with the simplest of all the difference of squares pattern, x squared minus 1. You can tell it is a difference of squares because both values are perfect squares and are being subtracted. This is the first step, recognizing this pattern. To factor it out, set out two empty parentheses, with a plus in the first one and minus in the second one. It really doesn't matter which one goes first, but traditionally the plus goes first, so we'll stick with that. Put the square root of x squared, the value x, in the first positions of each binomial, and then the square root of 1 in the second positions. And as simple as that, you have the correct factorization of this difference of squares example. Let's try another one. Here we have x squared minus 16. Set out the two binomials with plus and minus operators, put x in the first positions, and the square root of 16, the value 4, in the second positions, and behold the correct factorization. Here is one with an x squared coefficient other than 1, 4 in this case. We see that it fits the pattern of the difference of squares, since both terms are perfect squares, and they are being subtracted. We follow the same process of setting out the plus and minus binomials, put the square root of the first term, 2x, in the first positions, and the square root of 9, the value 3, in the second positions. And there you have it, the correct factorization of this difference of squares. Let's practice a few. In this first example, 9x squared minus 25. Think about the square root of 9x squared, 3x, the square root of 25, 5, and put it into the pattern, 3x plus 5 times 3x minus 5. In this next one, 16x squared minus 4, the square root of each term, 4x and 2, put it into the pattern, 4x plus 2, 4x minus 2. Here we have 25x squared minus 81, which factors to be 5x plus 9, 5x minus 9. 49x squared minus 1, square root of each term, 7x and 1, put it into the pattern, 7x plus 1, 7x minus 1. X squared minus 64 factors to be x plus 8 and x minus 8. X squared minus 25, x plus 5 and x minus 5. X squared minus 49, x plus 7, x minus 7. X squared minus 100, x plus 10, x minus 10. 81x squared minus 16. Square root of 81x squared is 9x. Square root of 16 is 4. The pattern is 9x plus 4, 9x minus 4. And finally, 36x squared, which factors to be 6x, minus 9, which factors to be 3. Final pattern, 6x plus 3, 6x minus 3. And now you know how to factor the difference of squares pattern.